Okay, so we kind of worked our way through our structure of CO2 here. It got a little messy in there, but I think maybe we got all the information there to figure out the correct structure for CO2. Now, formal charge, I think, is worth going into a little bit deeper here. So what I have here just a separate blank piece of paper. And what I want to do together here is let's build a little table addressing this issue of formal charge because we know from the structure of the periodic table there's a lot of trends, there's a lot of similarities, right? We're really not looking at a whole lot of variability in terms of valence electrons. So we have some nonmetals with 4, some nonmetals with 5, some nonmetals with 6, some nonmetals with 7. That's about it. So if we can get an idea of kind of the trends as a valence electron relates to formal charge, we can really kind of simplify our evaluation of what we're looking at. So what I want to do here is across the top, I'm just going to use the atoms that are good representations of the different columns in the periodic table. So let's think about a carbon atom, a nitrogen atom, an oxygen atom, and a fluorine atom. Okay. And there's also boron as a nonmetal, but boron has 3 bonds. That makes it a little unusual in terms of structure. We'll talk about that kind of toward the end in the things to watch out for segment. Hydrogen just has 1 valence electron. We can talk about that as well. But the vast majority of atoms we're going to encounter are these 4 atoms, or the ones that come beneath them that still have the same number of valence electrons, like silicon, phosphorus, sulfur, chlorine. Right? They've got the same number of valence electrons as each of those elements. Now, as the elements get bigger, there are some other things to think about, but this is a good place to start. Now, the other kind of axis of this table, I want to think about potential structures. Right? If we limit ourselves to the octet rule, right, which we're doing so far, there are only a couple of different ways, a few different ways, maybe is a better way to say it, that we can get to 8 electrons. So down this side, I'm going to draw an atom. So I'm just using A to represent the atom here, but each atom in a different table. Right? One way to get to 8 electrons would be to have 4 different bonds. Right? Now, for the purpose of the table, it doesn't matter what it's bonded to. It's got 4 bonds, it would have 8 electrons. Another way would be to have 3 bonds, right? And then a pair of non-bonding electrons. That would get us to 8 as well. If the atom has 2 bonds, it would need 2 sets of non-bonding electrons. And if it has 1 bond, then it would need 3 sets of 2 non-bonding electrons, or 3 lone pairs, right? And that's really it. You could get to 8 electrons by having 4 lone pairs, 4 sets of non-bonding electrons, 8 total non-bonding electrons. But if that's the case, you don't really have a molecule anymore because you're not bonded to anything. You might have an atom or an ion in particular, like a fluoride ion, but that's not a structure we need to worry about because there's no connection to any other atom. So that's really the only possibilities. Now, in the middle of the table, what I want to do is calculate the formal charge. So if a carbon looks like this, how would we calculate its formal charge? So formal charge, right, for carbon starts with 4 valence electrons. This structure would have 4 bonds and 0 non-bonding electrons. So this would be a 0 formal charge for carbon. So that is the ideal way for carbon to show up in a structure, is with 4 bonds. Now, that could be 4 single bonds, it could be 2 single bonds and a double bond, it could be 2 double bonds like we saw in carbon dioxide, right? You could have structures where you have a triple bond and a single bond, right? Even though that's not right for carbon dioxide, it could be right for other structures. But 4 bonds to our carbon, that's ideal for a carbon. Now, we might see a carbon that looks like this in a molecule. Well, what would be the formal charge here? Right? Still 4 when we start with carbon, since carbon starts with 4 valence electrons. But in this structure, there's 3 bonds, and there's 2 non-bonding electrons. So 4 minus 3 minus 2 is -1. Possible, right? We will see a carbon like that occasionally. But if we can avoid it, right, and make our carbon look like the top structure, that would be a better way to proceed. But we will see carbons like this occasionally. And again, I've mentioned this before, but this is a good indication that that is not the most stable carbon. So we might be able to predict this is possibly a reactive molecule. And if possible, that carbon would like to not have that lone pair and instead have a fourth bond. So that carbon might be likely to attach to something, use those two electrons to make a bond. Okay. Now, if you draw a structure and you see a carbon that looks like this, that would mean your formal charge, 2 bonds here, 4 non-bonding electrons, is -2. Never, ever have a structure with a formal charge greater than 1. If you see a -2 in your structure, it is wrong. It is, you did something wrong, you counted electrons wrong, you drew things wrong. So don't ever make that drawing, right? And it gets even worse down here. This would be the formal charge. 4 for carbon, 1 bond, 6 non-bonding electrons. This would be -3. That is never going to happen as well. Okay, now let me to give you an analogy here. If you're familiar with the Harry Potter series, if not, I'm sorry, but there's going to be spoilers. In this series, the bad guy, Lord Voldemort, tries to make these things called Horcruxes so that he can't die. So to make a Horcrux in the world of Harry Potter, you commit some unspeakably horrible act like murder an innocent person, and that breaks off a chunk of your soul. And you can magically take that chunk of soul and incorporate it into kind of an inanimate object, right? Or we see in the books also into another living object like a snake. But that chunk of soul will then tether you to this mortal world. So if the rest of your soul does happen to get killed, your body gets killed, that soul will keep you here, and then you can be revived from that piece of soul, right? So that's a fictional story. But in the chemistry world, right, how do you make a Horcrux? What is the unspeakable, horrible act that would cause a chunk of your soul to be torn off? It's drawing a carbon that looks like one of these structures, right? It's drawing a structure with a +2 formal charge on an atom or a -2 formal charge on an atom or worse. So don't do that. I don't want to spoil it. It doesn't work out so good for Lord Voldemort making the Horcruxes in the story, but I don't want to spoil it if you haven't seen it. So, but don't do it on your structures. Okay, what happens and how do things change if we move over to nitrogen? Well, the difference is the number of valence electrons, right? How we would start the formal charge calculation. So if we draw nitrogen like this with 4 bonds, that would be 5 - 4 - 0, and that would be +1. And that's okay. It's not great, but we will see that occasionally in structures of nitrogen with a +1. But right here, 5 - 3 - 2, that is perfect for nitrogens. So when we're drawing structures, we might want to think, hey, if I've got a nitrogen, I would really like if it ends up like this with 3 bonds and a lone pair, because that's going to give me a 0 formal charge. That is what nitrogens would really want to look like. Right, if they had desires about how they look. More stable is a better way to say it. If you draw nitrogen like the third one here, 2 bonds, that would be 5 for the valence electrons of nitrogen, -2 bonds, -4 non-bonding electrons. That's -1. That's okay. We'll see nitrogen like that occasionally. It does tell us that's kind of an angry nitrogen that's likely to engage in reactions. But don't draw a nitrogen like the bottom one. 5 - 1 - 6, that's a charge of -2. Don't ever do that to your nitrogens. Okay, so you can maybe see a trend here. There's the best one is where we end up with 0, right? And when we move to oxygen, the calculation is going to change because now it'll start with 6, right? So 6 - 4 - 0, this would be a +2 oxygen. That's a Horcrux. Don't do that. But 6 - 3 - 2 would be -1. That's possible, right? Particularly oxygen is highly electronegative. There'll be structures where it has a -1 formal charge and it'll be reasonably stable that way. But oxygens really would be best if they look like this structure here. 2 bonds, 2 non-bonding pairs, because that's 6 - 2 - 4. That equals 0. That is the ideal way to draw an oxygen. Okay. Okay. Now we could also see an oxygen that looks like, actually I did a math error up here. Let me fix that real quick. +1 there for oxygen. That's still possible, right? 6 minus 3 minus 2 is +1, not -1. That's possible, right? Not great for an oxygen because it is electronegative, but we will see that occasionally. The a little bit better non-zero for an oxygen is the last one. This is where we have 6 minus 1 minus 6. This is the one that's really equal to -1. And for oxygen being highly electronegative, yeah, this is okay for oxygen. We will see that in the structures. Okay, fluorine, we switch to 7. So 7 minus 4, that's a +3. Okay, that's terrible. Don't ever do that to fluorine. 7 minus 3 minus 2, that's +2. That's also terrible. Don't ever do that to fluorine. 7 minus 2 minus 4, that's +1. Now, don't ever do that to fluorine, right? Fluorine, we said, is the most electronegative element there is. You cannot force fluorine to have a positive charge because there's no other element that can pull the electrons away from fluorine to make the fluorine be positive. So don't ever do this to fluorine. You could do this, +1 formal charge, to the lower elements in that column, chlorine, bromine, iodine, but you can't do that to fluorine. So in your structures, fluorine should always look like this: 7 minus 1 minus 6, 0. So your fluorine should have 1 bond and 3 pairs of non-bonding electrons, right? As the elements get less electronegative, we can kind of move them into these less, well, at least this less stable arrangement here with the +1 charge on the fluorine, but you cannot do that to fluorine. So fluorine is always either 0 or it's by itself, in which case it would generally have the -1 charge of the anion. Okay, now we want to kind of keep this all in mind. This is something we're always going to be applying to our structures, right? And based on the number of possibilities, this is something you should be able to calculate relatively quickly just by looking at a structure once you've had a little bit of practice. Now, real quick, before I close off this video, hydrogen, right, only has 1 valence electron. So the calculation for hydrogen always 1 minus whatever, right? So if we draw a hydrogen with 1 bond, that's 1 minus 0 equals 0. That is perfect. Give your hydrogen 1 bond. It is a 0 formal charge. It is all good to go. So in your structures, keep that in mind. Connect 1 bond to your hydrogens and everything is fine. Okay, stop there. We'll come back and we'll pick up with some of the other structures.